Okay, this is my super brief introduction to measurement and uncertainty. Let's go. This is a picture of Plato's allegory of the cave. So Plato says, we don't really see the truth, that object being the truth up there. All we see is a shadow of that on a wall. So we don't really get to it. And this is really important for science because it's a lot like the way we do science. We don't actually know the values of things directly. We have to make measurements, but we use imperfect instruments. And that's like this imperfect shadow. So we have to learn how to deal with these imperfections. And that is what we call measurement and uncertainty. This is a normal distribution. Suppose I went out and I measured the height of a whole bunch of people and I plotted them. Some people there'd be an average value right in the middle of that plot, and some people would be very, very, very tall, and very few people would be very small. But most people are around the average. So we can use the idea of a normal distribution to represent data. So we're going to represent a number with its average, which is the middle of that distribution, and the standard deviation, which tells us how wide that distribution is. So let's say I have the length of something. The way I want to report it in physics is length is 3.14, that's the average, plus or minus 0.04 centimeters, that would be the standard deviation. And in general, we write that as the average plus or minus the uncertainty, where the uncertainty is delta L. So the question is, how do we get that delta L? I mean, I think it's okay to get the average. Everyone understands that. And we could get it with the standard deviation, or there's another way. So here's something that's a little bit trickier. Here's the diameter of this ball. If I measure the diameter of this ball with this ruler, I get 5.1 centimeters plus or minus 0.1 centimeters. But where did that plus or minus 0.1 came from? The answer is I made it up. So I, as a human, I can't repeat this measurement a bunch of times and get the uncertainty. So instead, I'm just going to approximate the uncertainty. I know the ball is not perfectly spherical, so it doesn't have one diameter. I know it's difficult to line that ball up with a ruler, so there's that. And there's also parallax issues. The ball's closer than the ruler, so it's a tough situation. The smallest that value can be is half of the smallest division. So in this case, the ruler goes down to 0.1 centimeters. I could go down to 0.05 centimeters for the uncertainty, but I don't think that's appropriate. I use my best judgment. So if you can only measure it once, use your best judgment. If you can measure it multiple times, do that. So suppose I drop a ball 7 times, I can find the average, and that would be my value. I can also find the uncertainty based on the standard deviation. So here's a way to do it in a spreadsheet. You can use your calculator. You can use online calculators. There's an equation. I doubt you'll do it by hand. So there's several options. So that's it. So the two ways to get the uncertainty is approximate it or with standard deviation. Now what do I do with that? Suppose I want to calculate something. I want to calculate the area of this square. So that's length times width, but the length and the width both have uncertainties. So how do you get an uncertainty in the area when you don't measure the uncertainty? Well, one way is with this crank 3 times method I'm going to show you. There are lots of ways to do it, okay? But this is the one that's, I think, the easiest. So the crank 3 times, the first thing you do is you calculate the area. So if you look here, the area is just 3.12 times 6.62, and you get 20.65. Now I'm going to calculate the maximum area. The maximum area uses the maximum width and the maximum length. So the maximum width is going to be this 6.62 plus 0.1, and the maximum length is 3.12 plus 0.03. And so then I get that maximum area. I got those backwards. I got the max and the min backwards, but you get the idea. So I can do the same thing for the minimum. And then the uncertainty is just going to be the maximum minus minimum divided by 2. So in the end, I get 20.6 plus or minus 0.5 centimeters squared. The units are important. What about this case? I have a flag going through a photo gate. I measure the width of the flag, and I measure the time interval, both with uncertainty. So in this case, I can calculate the velocity as the width divided by the time interval. But what about the uncertainty? To calculate the maximum velocity, I can use the maximum position, but the minimum time, because I'm dividing by the time. So dividing by a smaller time gives a larger velocity. So you see that in the end, and that's the reverse is true for the minimum. Okay, so what do you do with the uncertainty? It's really used to compare values. If I get two things, 0.31 seconds and 0.33 seconds, are they the same? Who knows? Okay, just that alone doesn't tell us. With uncertainty, we can make a comparison. Here's a picture. So the top case are two times on a timeline. T1 plus or minus delta t and T2 plus or minus delta t. So we have a range of values. I represent those with the arrows. If those ranges overlap, the dot's the average. If the ranges overlap, then I'm going to say they could be the same. If those ranges do not overlap, then they are probably different. And that's enough of measurement uncertainty for now.